I did a video on a beautiful continuous function statement, and Moira suggested in the comments a version of the statement that was true, and I'm going to prove that in this. So thank you so much to Moira for that suggestion. So the statement is that let f from 0, 1 to r be a continuous function so that the only solutions to f of x equals f of 0 are x equals 0 and x equals 1. So we'll uncode all this visually, okay? So what it's saying so far is that f of 0 is equal to f of 1, and so only time f of x is equal to f of 0 or f of 1 is when x is 0 or when x is 1. In that case, for any a, just fix an a. Okay, give me your favorite a between 0 and 1. F of x plus a is equal to f of x for some x in the interval 0, 1. So how do we visualize this? So basically the earlier video, and I'll link that at the end because it's quite a different proof and it's quite beautiful, is that here we have a function so that it's the same value at 0 as it is at 1. Okay, it's a continuous function, and we're given that the only time f of x is equal to the value at 0 or 1, so this is the y value, f of 0 is equal to f of 1. The only other time f of x equals to f of 0, f of 1, there's no other time. Okay, so basically we're given that. Now we want to show that if I give you some a, okay, let's say a is some really small number, okay, it doesn't really matter, or big number, okay, a could be something like 3/4, okay, it doesn't matter, a is 3/4. Now if you draw the graph of the function, then whatever it is, it could wiggle, it could go like this, etc. There's always going to be an x, so that f of x is equal to f of x plus 3/4, okay, so it could be somewhere like this and this point, right, I don't know, I mean it's not perfect. You could say this is x and this is x plus 3/4, and you could say that their y values are the same. F of x is f of x plus 3/4. It doesn't really matter what a is. A could be anything. Now this is not true. So the other video, it's not. You'll see that this property is not true if a is if this condition is not satisfied. Okay, if f of x equals f of 0, the only solutions are not x equals 0 and x equals 1. It may not be true. We can find two numbers a apart that have the same y value, okay, but that video will address that question. But here basically one important point to note is because the only time f of x is equal to f of 0 or f of 1, the only time is basically at 0 or 1, the graph can only, if it goes above, if it goes up, it cannot ever drop down. Okay, because if the graph ever dropped down, I'll draw another graph, if it actually dropped down, this would be another value where the value of f at that point would equal to the same value as f of 0 and f of 1. So that's not possible. So the graph has to be entirely above or the graph has to be entirely below. We'll rigorously prove that, and we'll rigorously prove this statement. Okay, so let's just dive into it. So statement 1 is what I just said. Okay, so statement 1, I'm going to prove, write this down. Statement 1 is that f of x is greater than f of 0 equals to f of 1 for all x, or f of x is less than f of 0 equals to f of 1. Okay, so for all x in the open interval 0, 1, which means between 0 and 1. Okay, so we're going to prove either of these two is satisfied. So that's an elementary proof. So let's actually just write that out. I'm going to do it on this side of the board. All right, so how do we do that is assume that the statement is false. Okay, so if it's false, that means there is some x1. Okay, so the proof of that statement, proof of 1, and I'm just trying to show you rigorous calculus proofs. Okay, this is like beautiful math. You know, it's a very creative observation that Moira made as well. But this is actually beautiful math. Like now we've got this observation. That's actually part of the main difficulty. Now, how do we prove it? So how does a rigorous proof goes? So we're going to say that assume that's false. So what that means is that there's going to be some x1, okay, so assume, so I'm going to say assume it's false. Now what we're going to do is we're going to say that there's some x1, so therefore there exists x1, okay, so we're going to say 0 less than x1 less than 1, so that f of x1 is greater than f of 0, and there's going to be x2, so there's going to exist an x2 between 0 and 1, so that f of x2 is going to be less than f of 0. Okay, and now because of this, the intermediate value theorem, f is continuous. Okay, so therefore the IVT implies that therefore there exists some point between x1 and x2, which is also going to be between 0 and 1 strictly. So there exists some x such that f of x is equal to f of 0 by the intermediate value theorem. Just like we saw there, you know, if there's some point where the graph is above, some point where the graph is below, it has to, if it's continuous, it has to cut this imaginary line where all the y values are f of 0, f of 1. So that's going to be a contradiction to our hypothesis. There's only one solution or two solutions to f of x equals f of 0. It's a crucial hypothesis. Okay, so now we've got that. The graph is entirely above or entirely below. we can actually now rigorously prove the statement, and it's a beautiful trick. So I'm just going to do that. Don't forget to smash that like button and hype the video if you're enjoying it. Makes a huge difference. I'm so grateful for all the support on the channel, everyone who's been watching and liking, commenting. I love to hear your thoughts. Makes a world of difference. It really motivates me to keep going because I'm trying to create a library of infinite free accessible math education. There's a lot of stuff to do, and I'm just going to power through it, and I love making this content. And so let's just get into it now. All right, so now let's get into it. So we're going to define a function. We want to prove that f of x plus a equals f of x for some x, okay? And we know a is fixed. A is a fixed constant. A is some number between 0 and 1. So how do we prove it? Just like all intermediate value theorem statements, you want to find a solution. What you do is you define a function g of x is equal to f of x plus a minus f of x. Okay, that's our function. Now we can sort of intuitively see, no matter what a you pick, you may be able to see on that graph that there is going to be an x so that f of x plus a is f of x, but we have to rigorously prove it. It's pretty beautiful. So how are we going to do this? So we've got this function g of x. Now what we're going to do is we're going to look at two values. Okay, this is going to be nice. So we're going to look at the value. So g is a continuous function on the interval 0, 1 minus a. Okay, because you have to define x plus a has to be in the domain of f, and x has to be in the domain of f. And the domain of f is the closed interval 0, 1. So here you observe g of 0 is equal to f of a minus f of 0, right? That's what g of 0 is. And g of 1 minus a, I'm going to pick this. Okay, 1 minus a, you'll see why. 1 minus a, you plug in for x. You're going to get 1 minus a plus a is 1. So you're going to get f of 1 minus f of 1 minus a. Okay, now here's the cool thing. We know that the graph of f was entirely above, this horizontal line. So all the f of x's were either greater than f of 0, all the x's f of x was less than f of 0. It doesn't matter which one. Okay, pick one without loss of generality. It's going to be symmetrical. Okay, so what you observe is that if the first case, let's say that this was the case. Okay, so f of x greater than 0 for all, f of 0 for all x in the interval 0, 1, then in that case this is going to be positive. But f of 1 is of course equal to f of 0. That's an important assumption. Again, these are all important assumptions, otherwise the statement is false. Good to think up counterexamples and drop them down below in the comments. That would be nice discussion. So f of 0 minus f of 1 minus a. In this case you're going to have, because again all the f of x's are greater than f of 0, this is going to be now a negative number. Okay, so it's going to be negative, and so therefore the intermediate value theorem guarantees that there is an x. So therefore there exists x such that g of x is equal to 0, and that's our desired solution. That's when f of x plus a is f of x. Pretty cool, right? So here's the video. You can watch it. It's going to actually establish the same property, that f of x plus a is f of x for some x if f of 0 is f of 1, but only for a equal to 1 over n where n is a natural number. And that requires a different reasoning. Beautiful video. You're going to love it. Check it out here. It's going to pop up on the screen. And another fun video you're going to love. Can you find a function so you differentiate once, differentiate twice, differentiate 3 times, you get back the function. So you don't get it back when you differentiate once or twice, but you get it back when you differentiate the 3rd time. It's actually pretty cool, and I explained from scratch. Okay, this is just an intro to differential equations without any differential equations in it really. You're going to love that video. Check it out.